So as we said in the previous video, counting sort allows us to sort n objects in theta n time, but let's think very carefully about the runtime. So the first thing I want to ask you is, let's say we want to sort an array of the 100 largest world cities by population. And you have two choices, quicksort and counting sort, as we just described it. So I'd like you to think about which one you think has a better worst case runtime in seconds. So pause, think about it. And I think the key point here is not necessarily to get the right answer, but to get the right reasoning. So make sure you come up with at least a plausible reason before continuing. Okay. So it turns out, as you might have guessed, just the theme or the feeling of this, it's not actually counting sort, even though it has better asymptotic runtime. It is instead quicksort. So why is that? Well, in counting-based sort, if we take here the 100 largest world cities by metro area, sorted by alphabet, if we now try and sort by population, we'll have this annoying property that we need to build an array that is of size 37,832,892, which is the population of Tokyo, because we need to count all of the unique possible values that occur. And in this particular case, these cities, they'll always be either 0 or 1 for every single count, and Tokyo will be at the very bottom. Okay, so this is my big old count array, and eventually we can use this to form the sorted list of world cities, not shown. Okay. Now counting sort, because it has to build this gigantic array, that's going to take a bunch of time. Especially imagine in Java, where I need to actually initialize, in any language actually, if you build counting sort the way we've described it, we're going to have to build this big a big array, which has all these zeros and ones in it. It's going to take a long time. Okay, quicksort will be faster. All right. Now, if we have more items, if we have an arbitrarily large number of items, n items, then counting sort will actually be faster. But for this specific use case, we can see that counting sort will be slower because the relative size of the alphabet is tiny compared to the number of items. Okay. And by alphabet here, I mean the population of possible different keys, all the different values that could possibly occur. So rather than having spade, heart, diamond, and club, here we have 0, 1, 2, 3, 4, all the way up to 37 million. So it's a much bigger set of card suits, so to speak. In particular, almost 38 million of them. Okay, so question for you. What is the runtime for counting sort on n keys with an alphabet of size r? And here, I want you to treat r not as a constant, but as a variable. Okay? Because as we just saw, depending on the size of your keys, it can affect the runtime, the size of your alphabet, that is, the size of the different values that can occur. So I will wait here, and you can try and think about the runtime for a little bit. This is a less interesting question, but I think still worth your time to try. Okay, so it turns out the runtime is going to be n plus r, in particular theta n plus r. And how does that work? Okay, well, we could just go through each step. So the first step is we create an array of size r to store the counts. That takes theta r time. So for card suits, that will be 4. That will be the size of my array. I then count the number of each item, and so that takes theta n, because for each item, I'm going to go increment the appropriate array entry in my count array. So that's theta n. I will then calculate the target positions, or the starting positions, and that will take theta r time, because it's just the cumulative sum. We didn't really talk in detail about that operation, but it's just theta r. We build another array where each entry is equal to the sum of all entries above it. And that takes theta r time. Then I'm going to create an array of size n that stores the ordered data. That's that last piece. There's theta n. Then I'm going to copy the items from the original array to the ordered array, and that requires us to do the following n times. First, check the target position. So I look in the array that tracks the starting positions, or the target position, and that will be theta 1. I then update the target position, and then I also have to copy the items. I guess I lift it off in this step, but I also need to copy the items. That's also theta 1. And then at the very end, assuming that we actually want to change the original array, we will copy everything from the final array back to the beginning, theta n. Okay. In terms of memory usage, that will be theta n plus r because I need to create 2 arrays of size r and 1 array of size n. Okay, so that's the runtime analysis for counting sort. So the bottom line is that if n is bigger than or equal to r, then we expect reasonable performance. But if r is really, really, really big, like the example of sorting world cities, then it won't be so good. So just to note, in terms of memory usage, this n is for the ordered array that we build, and r is for the counts and the starting points. And if you wanted to know which one's actually better, then we need to do some kind of experiments, say versus Quicksort, to see which is better. And we won't do it in this lecture, but in the next lecture we will actually do a deeper comparison of so-called counting sorts and a couple related sorts we'll talk about later today, and our earlier comparison-based sorts. Okay. So that's counting sorts runtime in a few words, and hopefully this makes sense. I think this is a pretty straightforward runtime analysis. There's a lot of little pieces to keep track of, but there's nothing tricky here like there was with, say, merge sort or Quicksort's runtime analysis. To see if this runtime analysis makes sense, I'm going to ask you a question which may or may not be a trick question. So let's say we'd like to sort really, really, really big collections of items from some alphabet, say card suits or integers or whatever. Which algorithm is going to be the fastest? Counting sort or Quicksort? Okay, it's just counting sort. So counting sort's runtime is n plus r, and Quicksort is n log n. And for sufficiently large collections, if we just eventually have a big enough n, counting sort will simply be faster. Even sorting integers, even though r is a really big number, if n is much, much bigger than the set of integers, well then counting sort is going to be the winning choice. All right, so to summarize all of our sorts, we have our heap sort, insertion sort, merge sort, and randomized Quicksort here. So these are all different versions of the sorts we saw before. And now we have a new tool called counting sort, which takes n plus r memory and n plus r runtime, but it only works if our keys come from some kind of an alphabet. So it turns out that there are some things that don't really match the definition of an alphabet. Consider, for example, all strings. So strings, there's a countably infinite number of strings out there, and as a result, that means that we cannot, you can't just say they're all from some alphabet. It wouldn't make sense because there's an infinite number. And so that means that what we have so far, counting sort's cool, but we couldn't really use it without being a little bit hackish in how we implement it. We couldn't really implement it with strings. And so what we're going to see in the coming videos is how we can generalize counting sort to go even beyond alphabet keys. And that will give us what will be known as a Radix sort.